Okay, so the binomial theorem. This is one of my favorite things to teach, actually. Okay, so the binomial theorem is this crazy thing. So x plus y to the nth power is the sum of the terms of n choose k of x to the n minus k and y to the k, where n choose k is n factorial over k factorial, n minus k factorial. What the heck, right? First time I looked at that, I was like, excuse me, like I can't do that. You can, but let's go over what some of this means. So that E looking thing right there, that means summation. And summation or sum in math is when you're adding up all the terms. So it's the terms from k equals 0 to whatever n may be. So it's from 0 to whatever this power right here would be. So it could be like 5 or 10 or 400 or whatever, okay? I would never give you something super crazy. And then this means combination. And it's how many ways we can choose k things from a total of n samples. Okay, so say you had like a total of 7 books, and we wanted to see how many different groups of 3 could we put these 7 groups into. Okay, and that's what this n choose k thing is. So that's the n factorial over k factorial n minus k factorial. What the heck, right? When someone explains, yeah, that's what you probably look like right now. This binomial theorem is a formula for finding any power of a binomial without multiplying it at length. So kind of what we've been doing, so I've been having you guys like square things out. So say you have like x minus 4 to the 4th power, and we have to write it 4 times, multiply it all out, right? Okay, let's get into this a little bit more. This is a shortcut to do this. So let's use this yucky formula to expand one of these. So this is an example in your notes. A plus b to the 3rd power. Well, let's plug that in. So we have, I'm just plugging in 3 where I need to, and that's really going to be, I did this wrong. That should be a, and that should be b, the x and y. So in your notes, all I want you to do right now is change that to an x, change that to a y. Okay, change that to an x and y. I can't get my pen to stay. I'm just a little challenged with technology, but change that to an x and y, okay? So let's do this. And we're just gonna plug this in. So we have 3 choose 0, because I'm plugging in 0 for my k first. So I'm plugging in 0 for k first. So 3 choose 0, then we put a 0 here and a 0 there. That's where this one comes from. Okay? And then we're gonna plug in 1. So plug in 1 right there, plug in 1 right there. That's where this one comes from. Plug in 2. That's where this one comes from. Plug in 3. That's where this one comes from. Okay? And then let's start to simplify this down. Yeah, what the heck are those exclamation points? Why do we have exclamation points? So an exclamation point, because we need to simplify this piece right here. An exclamation point in math means factorial. And these are actually kind of cool. So factorials are, says to multiply all the whole numbers down to 1. So an example of that would be like 4 factorial is 4 times 3 times 2 times 1, which equals 24. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 3,628,800. Okay? Well, now let's use that, and those factorials, this gets into stats and a bunch of crazy stuff, but these factorials are used to figure out how many ways you can choose certain things. Okay? So let's do the 3 choose 1. Oh wait, sorry, the kicker. 0 factorial equals 1. Okay, and it's very similar to the n to the 0 power equals 1. So anything to the 0 power equals 1. 0 factorial also equals 1. These two things right here are very, very important to remember. I would write these down in your notes. Okay. Now let's get into this. So 3 choose 0. That's 3 factorial over 0 factorial and 3 minus 0 factorial. So 3 factorial is 3 times 2 times 1. 0 factorial is just 1, so we don't have to do anything with that. 3 minus 0, that's 3 factorial again, which is 3 times 2 times 1. Which those all cancel, so you're just left with 1. So that becomes a 1. Okay, 3 choose 1, so that's 3 factorial over 1 factorial and 3 minus 1 factorial. I skipped something. This should be 3 times 2 times 1, and this should be 2 times 1. Because the 3 factorial on top, and this ends up being a 2. The 2 times 1 right there cancels. So all you're left with is 3. And that's 3. 3 choose 2. So that's 3 factorial over 2 factorial. This becomes a 1. So that's going to be 3 times 2 times 1 over 2 times 1. Again, those 2 times 1s cancel, and you're left with 3. So that becomes a 3. 3 choose 3 factorial, so that's 3 factorial over 3 factorial, 3 minus 3 factorial. This right here becomes 0. So that's just 3 factorial over 3 factorial, which is going to cancel itself, and you're just left with 1. Cool. Now all we have to deal with is our powers, okay? So that's a 3. Anything to the 0 power is 1, so that first y goes away. That second one, 3 minus 1 is 2, then y. 3xy squared, and then y cubed. I don't want to do that every single time. There's too many formulas, right? That's way too many formulas to remember. I don't like doing that. So there's got to be an easier way. Let's look at this one with our basic understanding of multiplying polynomials. So this is what we have been doing, is just multiplying them out. So we have c plus d to the 5th power. So that means we have c plus d 5 times. So let's multiply those two. You get c squared plus 2cd plus d squared, which is the same as those two right there. So now let's multiply those two big ones. So you get c squared plus 2cd plus d squared, and then c squared plus 2cd plus d squared. So it's getting ugly already. So you end up with c to the 4th plus 4c cubed d plus 6c squared d squared plus 4cd cubed plus d to the 4th. Oh my goodness. Now let's do that one. This is the last one. And you get c to the 5th plus 5c to the 4th d plus 10c cubed d to the 4th. That was wrong. This should be squared. This should be squared. Sorry, full of typos. 10c squared d cubed, 5c d to the 4th, and d to the 5th. Very ugly. Okay. I don't ever want to do that again. There has to be something better that we can do. So there's this thing called Pascal's triangle. And I want to build this triangle. Make sure you write this down somewhere. Okay. So we start with an infinite number of zeros. It goes on forever, 0, 0, 0, and then we have a 1, just right in the middle, just a 1. And then all the zeros continue to go on forever. The next row, we're going to add up the two numbers above. So you can add up, like, 0 plus 0, that's going to give you 0. 0 plus 0, 0. 0 plus 0, 0. But then 0 plus 1, that's going to give you 1. 0 plus 1, that's also going to give you 1. And then 0 plus 0, 0, so that's all the zeros. Continue to go on forever in those directions. Okay, let's do it again for the next row. So we have 0 plus 1 here equals 1. 1 plus 1 equals 2. 0 plus 1 equals 1. Okay, if you kind of get what we're doing, pause it and continue, or just continue with me. So the next row would be 0 plus 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0 is 1. And then the zeros continue forever. You'll always have zeros. Okay, this next one, 0 plus 1 is 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 0 is 1. And this continues forever. You can do this forever. Okay, and that is the triangle right there. And this triangle is super crazy. It pops up in nature all the time. It's in like ancient architecture. These numbers have popped up if you are interested in ancient architecture. I am. They're very cool, like the pyramids in Egypt. These numbers are all over those pyramids, and that's kind of crazy. But anyways, so this triangle is Pascal's triangle, and that's what we've named it in this Western world. We call it Pascal's triangle. And there's a bigger version of Pascal's triangle. So I'm just going to give you a little background. Sorry, this video is going to be a little bit longer than normal, but that's okay. So before we get into this, how it relates to binomial theorem, let's talk about a little bit of history of this. I never got the history of math when I was going through school, and after learning it and diving into this, I actually think the history of it is really cool. So in India, this was called the staircase of Mount Meru. In Iran, it was called Khayyam's triangle. I had to write that down because I didn't know how to say it. China, it was called Yang Hui's triangle. Italy is called Tartaglia's triangle. And then the Western world calls it Pascal's triangle after Blaise Pascal. But you can see that this triangle is all over. Okay, and there's crazy, crazy patterns to this. So like if you look at this first diagonal, it's all ones. The second diagonal is your counting numbers, so it always goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, forever. The third is your triangular numbers, which means that you can make a triangle out of them. So like 1, you can make a triangle out of that, I guess. Okay, 3, 6, 1, 2, 3, 4, 5, 6. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that continues, and you can do it with all of those. The fourth diagonal is the tetrahedron one. So that's a tetrahedron is a triangle that's three-dimensional. Okay. I'm not going to try and draw that because it will be super pitiful. If you add up the numbers of the rows, the sum of the digits will be 2 to the nth power. These are just cool patterns. You don't need to memorize these. These are just cool patterns. So like that first row is 1, which is 2 to the 0 power. The second row is 2 if you add them up, and that's 2 to the first power. Third row is 4, which is 2 to the second, and that continues forever. Pretty cool. And then the other one, there's so many, but the other one is if you just look at these as place values, it's 11 to the nth power. So like that first one is 1, which is 11 to the first, or 0 power. The next one is 10 plus 1, because that would be like the tens place right here. Tens place, and then the ones place. So 10 plus 1 is 11. 11 to the first power is 11. And this continues and continues. Okay, whoops. Pretty cool. There's tons and tons and tons of patterns. I'm going to put these links on the canvas if you want to go look at them. If you just search Pascal's triangle, super cool. Another cool thing to search is the golden ratio. Okay, anyways, I'll get off my math rant and let's actually get into like what we're going to be doing with Pascal's triangle. So let's look at some binomials here. So a plus b to the second power, that's a squared plus 2ab plus b squared. A plus b to the third power is a cubed plus 3a squared b plus 3ab squared plus b cubed. A plus b to the fourth power is a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. If you don't believe me, then you can multiply those out, okay? But let's look at the coefficients of these, the binomial coefficients. And a coefficient is the number that comes in front of the term, okay? So the coefficient of a plus b squared is 1, 2, 1, and that comes from here, 1, and then there's the 2, and then there's a 1. If there's not a number, you just assume it's 1. Okay, if we look at the Pascal's triangle, 1, 2, 1, that corresponds right there with the second row. Okay, and the rows always go, this is the, it's kind of weird, this is the 0 row, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can always look at the second number, and that will tell you which row it is. Okay, so the second power corresponds with the second row. Well, let's look at the third power. Does it work with that? So a plus b to the third power, that's 1, 3, 3, 1. That's the third row. What about the fourth power? 1, 4, 6, 4, 1. That's the fourth row. It's kind of weird. See how so by the Pascal's triangle really, really helps us in the binomial theorem because it gives us what those n choose k terms are going to be. It tells us what those numbers are. Okay, so the binomial coefficients correspond with the nth row of Pascal's triangle. Whoa. Okay, so let's fill this out a little bit more for you guys. So we have to the third row, so let's go to the fourth row. Yeah, 15th century, it's been around forever. I've gone on a couple rants about this, so I'm going to stop, but let's fill this out. So 1, 4, 3 plus 3 is 6. 3 plus 1 is 4, 1. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1. Okay? So x plus y to the 7th power. Now I'm going to teach you the easiest way I have figured out to expand binomials using binomial theorem, using Pascal's triangle, except for I'm not doing this summation thing. I am, but I'm doing it in a backwards way. So we're going to do it with boxes. I really like boxes. Okay, we're going to organize this with boxes. So if it's the 7th power, it's always one more box. So that means I'm going to have 8 boxes. Okay, so draw 8 boxes. Hopefully you have room on your paper. If not, just grab a scratch paper. Now, the first row is filled with the numbers from Pascal's triangle. So if we look at Pascal's triangle, go down to the 7th row, which means it's the one that has 7 as the second number. And we're going to put those in the first row. So 1, 7, 21, 35, 35, 21, 7, 1. And then we're going to have a second row. We're going to have 3 rows altogether. The second row is filled with the first term. Put them in parentheses. So the first term here is x. So it's going to be x, 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 all the way down. Now the exponents, we have to have exponents. On the first row, they start at 7 and they count down. So they start at whatever your power happens to be. So our power here was 7, so that's why they're going to count down from there. So this is going to be 7, 6, 5, 4, 3, 2, 1, 0. And then the third row, this is where you put the second term in parentheses. So this is going to be the y. And we ended at 0. So now we're going to start at 0. You end at 0, so you start back at 0. Not 0, 1, 2, 3, 4, 5, 6, 7. Okay? Now anything to the 0 power equals 1, so we cancel those out. Those are gone. And then we simplify these down. Okay? You can draw another row of boxes if you want. You don't have to. You could just write this out. The boxes help organize it though. So now we can multiply columns. So in that first column, we have 1 times x to the 7th, so we're multiplying down here. 1 times x to the 7th, which is x to the 7th. That next one, we have 7 times x to the 6th times y to the first, so that's 7x to the 6th, y. Next one, 21, x to the 5th, y squared. 35, x to the 4th, y cubed. 35, x cubed, y to the 4th. 21, x squared, y to the 5th, 7, x, y to the 6th, and then y to the 7th power. We have to put plus signs in between all these because remember, these are summations. The binomial theorem, it's the summation, that weird e. So our final answer is going to be x to the 7th plus 7x to the 6y plus 21x to the 5th, y squared, plus 35x to the 4th, y cubed, plus 35x cubed, y to the 4th, plus 21x squared, y to the 5th, plus 7x, y to the 6th, plus y to the 7th. Cool? Let's fill these out. So the total number of terms is always n plus 1. The exponent of a is always n. The exponent of b is always n. So in the first term, it's always n. The last term, it's always, for b, it's always n. The exponent of a decreases from left to right, and then b increases from left to right. And then the sum of the exponents in each term is n, and the coefficients are multiplied and follow the nth row of Pascal's triangle. Okay, this one we filled out most of it for you. I just want to simplify this. So we have 2x to the fourth power. So if we have 2x to the fourth, that's the same as 2 to the fourth x to the fourth. 2 to the fourth is 2 times 2 times 2 times 2. 2 times 2 is 4. 2 times 2 is 4. 4 times 4 is 16. That's where that 16 comes from. Okay. This next one, we have 4. 2x to the third power is 8x cubed, because that's 2 cubed, x cubed, and then 5. The next one, we have 6 times 4x squared. 5 squared is 25. Next one, we have 4 times 2x times 5 cubed, which is 125. And then 5 to the fourth is 625. Let's finish multiplying these out. So that's 16x to the fourth. 4 times 8 times 5 is 160, x cubed. 6 times 4 times 25 is 600, x squared. 4 times 2 times 125 is 1,000x. And 1 times 625 is 625. Put those plus signs, and so our final answer is 6x to the fourth plus 160x cubed plus 600x squared plus 1,000x plus 625. This is the last example, I promise. So here we have an exponent of 5, so we're going to have 6 boxes. The Pascal's triangle, so the terms from the 5th row go into there. So that's going to be 1, 5, 10, 10, 5, 1. If you forget which row, you just count how many boxes you have and then see which row has that many terms. Okay, the next row we're going to have 2x. The next row, oh yeah, and then so it's 2x to the 5th, and then count down 5, 4, 3, 2, 1, 0. And then -3, count up 0, 1, 2, 3, 4, 5. Anything to the 0 power cancels. And then we're going to simplify this down. So that's going to be 1 times 32x to the 5th, because 2 to the 5th, x to the 5th. 5 times 16x to the 4th times -3. Make sure if you're putting that in your calculator, you have to put it in parentheses, so it gives you the right sign. And then 10 times 8x cubed times 9, because -3 times -3 is 9. 10 times 4x squared times -27. 5 times 2x times 81. And then 1 times -243. Finish multiplying, so that's 32x to the 5th, -240x to the 4th, 720x cubed, 1080x squared, -810x, -243. So that's 32x to the 5th plus -240x to the 4th plus 720x cubed plus -1080x squared plus 810x plus -243. Anytime you add a negative, it's the same as subtracting. So adding a negative is the same as subtracting, so you can just change those to subtraction signs. Notice the alternating pattern in the signs. That always happens when it's subtracting. Okay, there will always be an alternating pattern in the signs when you subtract. Okay, let's see. Remember to take the quiz. We'll save the rest for class. I apologize for this being so long. The history of this is really cool. So yeah, but anyways, you guys are awesome. Thanks for sticking through this. I promise we'll go over some more examples to help solidify some things, but hope you're having an awesome day, and I will see you guys tomorrow, or whenever I see you.